Okay. All right. Hello, everyone. My name is Jennifer Bradley, and I'm the Adult Programming Librarian at the Clearview Library District. And it is my pleasure tonight to have with us Dr. Nicole Kelp. She is an assistant professor at the Microbiology, Immunology, and Pathology Department at CSU. And she's going to be talking with us tonight about the history and science behind vaccines and how they work with our immune systems. But before I get started, just wanted to remind everyone that, or ask everyone that if you have any questions, you can use our chat button feature at the bottom of your screen. For some people, it'll be a visible button. For others, you may have to click there's on my computer, there's a more section that you click on and you can see an option for chat. So, but feel free to put your questions or type out your questions in chat, and then we will address them at the end of the talk. Uh, or we will also open up mics at the end of the talk as well. And with that, though, I will now turn things over to Nicole.
Awesome. Thank you, Jennifer, so much for that introduction. I'm going to share my screen with a PowerPoint here. And I will apologize if my camera is kind of pixelating at the bottom of my video and we are not sure why, but hopefully my audio is clear and my PowerPoint is clear so we can talk about the COVID vaccine. Like Jennifer said, I'm an assistant professor in CSU's Department of Microbiology, Immunology, and Pathology. And part of my role is performing research on science communication and understanding how scientists think about and talk about science and how we dialogue with people who don't have a background in science, and empowering everyone to contribute to and be part of dialogue about science. So I'm really excited to be here and really look forward to especially the Q&A section and getting to be in that dialogue with you all. My teaching at CSU is mostly actually in the medical school branch. If you guys aren't aware, CU Anschutz is opening a medical school branch up at CSU. So I work with a lot of clinician colleagues, and we're putting together a new curriculum for the medical school. Before I was at CSU, I was at Washington State University, where I taught microbiology, immunology, and a vaccine development course. And so that's kind of my background that enables me to speak into this. But I think it's really important for all of us in this age of COVID, where we get all sorts of information from different people, to understand the expertise of the people we're listening to. And so I'll share what my expertise is and isn't. Like I said, I've taught microbiology and immunology, and I've worked in a lab using molecules like RNA, which is what makes up the COVID vaccine. However, I have not worked in a virology lab or developed a vaccine in a lab myself. And so for those things, I always defer to the scientific expertise of my colleagues who do specifically work on developing COVID vaccines. So I have a lot of relevant background here, but then also am relying on scientific consensus for other aspects of the presentation. So I titled my talk, "The Race to Create a COVID Vaccine. Was it a marathon or a sprint?" Because I think a lot of us might have the question, how do we get a COVID vaccine so fast? It's only been a year. It took decades to create other vaccines. Where did this come from? And so I think to answer this question, we can look at the science and history of how vaccines are developed, and then look specifically at the COVID vaccine. Try to get my screen to progress. There we go. So first, I'm going to talk about the immune system, which is a system in our body that fights against things like viruses. And we need to understand this to understand how vaccines work. So the first thing that's going to happen to activate your immune system is a pathogen, a virus or a bacteria enters your body. Here I have a picture of what the COVID virus somewhat looks like in cartoon form. Your body has cells that will recognize this foreign pathogen, and they're non-specific. They couldn't tell if this was a COVID virus or an influenza virus or a common cold virus. They just know it's not you. They know it's foreign. And they sound the alarm and say, hey, something foreign is in the body. We need to start a process to fight this. And they start a process called inflammation, which we've all experienced. That's redness, swelling, fever, pain. And that's your immune system trying to kill off this pathogen. Another component, like I mentioned, is fever, which your body does on purpose to try to kill off the pathogen. All of this is part of what we call innate immunity, meaning everybody has the same type of immune response to this, and it doesn't get better or worse depending on the pathogen, and it's not any different depending on different pathogens. It's very non-specific. Another thing that inflammation does, besides trying to kill off the virus, is activates this special cell called a dendritic cell. The dendritic cell is really important because it will pick up this pathogen, you can see a little virus inside it, and take it to your lymph nodes. And in your lymph nodes, it will activate specific immune cells called T cells and B cells. They're specific, meaning they only recognize one particular pathogen. So there's a ton of T and B cells in your lymph nodes. The dendritic cell will search through them and find the one that is active against that particular pathogen that your body is fighting. And then it will start multiplying and making a bunch of copies of that particular T and B cell. That's why when you get sick, maybe your lymph nodes in your throat start swelling up because they're making a lot of these T and B cells. Okay, what do T and B cells do? You have an active T cell, which I've indicated here with a star. It is able to kill viral infected cells. So it will look at that cell and say, well, this is me, this is self, but it's got a virus in it, so I'm going to kill it to keep that virus from replicating. B cells make antibodies, which are these Y-shaped molecules. And we've probably all heard about antibodies with COVID and other diseases. What antibodies do is they can bind to the virus or bacteria, whatever it is, and prevent it from infecting a host cell, or they can help other immune cells kill that virus or bacteria. So while they have many functions, T and B cells are basically going to inhibit and kill off this pathogen with a very strong specific response. Also, some T and B cells are going to become what is called memory cells. And memory cells will, like the name implies, remember that particular pathogen. So if you were to encounter it again, your memory would really quickly activate and you would get an even bigger, better, stronger response to these T and B cells, of these T and B cells to that pathogen. And so the second time you encounter something, you may not even notice you encountered it because your immune system will wipe it out before you even get sick sometimes. So this in the big picture is how immunity works. We have the innate immunity, which is nonspecific, and then the adaptive immunity, which adapts and changes over time to get more powerful and more specific against a particular pathogen. So that's how your immune system works naturally. How do vaccines work? Very similarly. You'll notice that here I have almost the same picture. The only difference is instead of you running into the pathogen in real life or in the wild, a wild type pathogen that is the full version of it, you'll just get a portion of this pathogen in some way, shape, or form provided by the vaccine. That enables your body to recognize that it's foreign, create the immune response, and have active T and B cells and memory that would then be able to attack and kill that pathogen if you do see the natural version of that pathogen that you're exposed to. And so this is great because you were able to build this memory without having been exposed to the pathogen in the first place. So you get the immune memory without the risk of disease symptoms. So how do vaccines harness this natural immunity? You'll notice that it goes through the exact same process as your immunity without the vaccine. You have inflammation, and this is why if you get a vaccine, your arm might be sore, you might get a fever. This isn't bad or side effects. This is intended. This is good. This means your immune system is being activated. So feeling a little under the weather after getting a vaccine just means your immune system is doing its job. We need that inflammation to activate these dendritic cells, to activate the T and B cells. You'll also remember that we talked about how the more that the memory cells get activated, each time they see the pathogen, the stronger that memory gets, the stronger the response gets. So that's why you might have a multi-dose series or booster shots of a vaccine. So your body gets some more practice responding to it. So if it is to see it, the full version of the pathogen, you're really primed to respond against it. So I said that the vaccine provides a portion of the pathogen. How does it do that? If you got the CDC childhood vaccination series, you got these 4 different types of vaccines. And these are kind of the traditional vaccine technologies, I'll say, that enable us to get a portion of the pathogen without actually getting sick. So the first version is The first version is called live attenuated, and that is where the whole pathogen is present, but it gets weakens. That's what attenuated means. It gets weakened so that you don't actually get sick. Your body gets to see the whole pathogen, make immunity against all different forms of the pathogen, but not actually get symptoms from it. However, there's the very slight chance that live attenuated vaccines can revert to their active form and cause disease. So to prevent that, there's different versions of the vaccine, or they've created different vaccine technologies where we have inactivated pathogen. Still the whole pathogen makes a really strong immune response, but it's killed, so there's no chance it can cause disease. Thirdly, we have the subunits. And so that's where there's just a small portion of the pathogen that your body makes a reaction against. So maybe a protein on the surface of that pathogen. And then finally, the toxoid or inactivated toxins. A toxin is a protein made by bacteria that causes symptoms. So like tetanus, the lockjaw and tremor and pain symptoms are caused by this tetanus toxin. If we give you a vaccine that's a similar protein, your body will recognize that and mount an immune response against it. So those are the 4 different traditional types of vaccines that we've probably all received. So what about the COVID vaccine? You'll notice here is a chart that was published showing 5 of the different types of vaccine technologies under development for COVID. You'll notice the 3 in the middle, live attenuated, inactivated, and subunit, are based on those similar technologies that we just talked about. So they already had this methodology and they just adapted it for COVID. The ones on the outside here, RNA and viral vector, are newer technologies that have been under development for other diseases like Ebola or Zika or dengue or Nipah or HIV. So various different viruses that researchers have been working on creating vaccines for. They were able to take those technologies and adapt them for COVID. So we haven't probably been familiar with them. The only licensed version before COVID was the Ebola vaccine for viral vector, which is being given in Congo and other places to eradicate Ebola. But unless you receive that vaccine, you probably aren't familiar with the RNA or the viral vector form of the vaccine. So let's talk about those particular forms. The RNA vaccine is like the Moderna and Pfizer vaccine that are already being used for COVID. Viral vector is the AstraZeneca and Johnson & Johnson vaccines that are soon to be approved, most likely. So these are ones that we should be familiar with how they work. So what are DNA and RNA, and what is a viral vector? Before we think about them in vaccine, let's just think about what they do in your body. Here's a normal human cell. You'll notice that you have DNA, which is your genetic code. Your body will transcribe that into something called mRNA and then translate that into protein. DNA doesn't actually do anything in your cell. It's just a code. RNA doesn't really do anything either, also just a code. It's proteins that really do things in your cell. So getting to protein is what your cell wants to do generally. So if your body sees RNA that's injected in a vaccine, it will say, hey, RNA, I know what to do this. I'm going to translate this into protein. If that RNA encodes a COVID protein, your body will then translate and make that COVID protein, which your body will say, oh, this is foreign, I don't recognize it, and mount that whole immune response that we talked about. And that's basically the principle of the Moderna and Pfizer vaccines. There's a concern that some people may have of injecting genetic material, RNA from a virus into me. Isn't that bad? Could that hurt my genome? The special thing about RNA is that it degrades really quickly. It's kind of annoying. I've worked with it in the lab and it's hard to actually keep it from degrading. So once it's in your body translates it and then destroys it. There's enzymes in your body that chop up RNA. So you don't need to worry about it messing with your genome because it doesn't. The Moderna and Pfizer vaccines are just this naked piece of RNA. The AstraZeneca and Johnson & Johnson vaccines are that piece of RNA in a coat or a package, which is basically a shell made from a different type of virus. Not a virus that can make you sick, it's just the outer coating of it. And it's basically a vehicle that helps get that RNA into your body. So once it's in there, it gets translated into protein and we get the exact same response. So they're very similar, it's just, is the RNA naked or covered in a coat? So here's this picture we've seen again of how vaccines activate your immune system. And with the COVID vaccine, there's just one extra step. The COVID vaccine provides a code for the portion of the pathogen. Your body makes that into the portion of the pathogen, the protein, which then activates this whole immune response that we've seen before. there's kind of a science of how immune system work, how vaccines work, and how the COVID vaccine in particular works. I want to talk about these three potential questions and concerns that lots of people might have. And then obviously, if you have other questions or concerns, you feel free to throw those in the chat and we can talk about those at the end as well. So first, how effective is the COVID vaccine? We need to think about what vaccines do and what they can't do. If you think about your immune system, here's your active T and B cells versus the pathogen. It's kind of like a battle. You have troops on both sides, the pathogen versus you. Vaccines give you a lot more troops. They strengthen your immunity. So that makes it so you're better able to fight that pathogen. It's still a battle though. It's not 100%. If you get a big old dose of pathogen, or if you have a weaker immune system to start with, there's a chance that maybe the pathogen will win for a little bit and you might get some symptoms. So no vaccine is 100%. Many of them are 80%, 90% effective at preventing symptoms, but they can't quite be 100% because all they do is beef up one side of the battle and there's still a battle going on. So how do those percentages for the COVID vaccine compare to other vaccines? Let's look at the actual data here from the Moderna and the Pfizer vaccine. So a lot going on. Basically, all you need to know is along this bottom x-axis here is time for when the people either got a placebo shot or the vaccine shot. On the y-axis is measuring the event rate, and the event they were measuring were people getting symptoms of COVID. For both charts, the line along the bottom is the people who got the vaccine. You'll notice there's very few events, versus this line going up on both charts is the people who got the placebo, meaning they got no vaccine. There's a lot of events. So they vaccinated or placebo shot the two groups, and then those two groups just went about their lives. They were exposed to COVID, community spread in the environment, and then they looked at which people actually got COVID symptoms. And 95% of those people were people who had actually not got the vaccine. They were in the placebo group. Only 5% of the people who got symptoms had been vaccinated. And that's why we know it's a 95% effective vaccine, which is more effective than many other vaccines. Like I said, a lot are 80 or 90% effective. So 95% effective is very good. And in terms of severe disease requiring hospitalization, all of those events were in the placebo group, which means nobody who got vaccinated got severe disease. So it's 100% effective at preventing severe disease, which is amazing. So these are very effective vaccines. There are some questions that remain to be answered though. When a person gets vaccinated, if they got exposed to COVID, what happens? Do they just not get infected? Their immune system is that strong because of the vaccine? Or is there a chance they get infected but are asymptomatic? So they wouldn't show up in those events because the events they were measuring was symptoms, not COVID positive. And if they're asymptomatic, could they be spreading pathogen to other people? That's why even once someone gets vaccinated, the CDC is currently recommending they still wear their mask, they still social distance, because there's a chance they could spread it to other people. They're protected from getting severe disease and symptoms, but other people might not be yet. And so it's still good to be exercising those precautions. It's likely that this is the option, that the vaccine is good enough that the person doesn't get infected, but we need to do more research to test all of the vaccine recipients and see if there's actually COVID positive but asymptomatic people. So more research needs to be done here. Another question that researchers are continuing to analyze is how long does this immunity last? And this is something we just haven't had the time to answer that question, right? It's only been a few months since these vaccine trials. Does it only last a few months? Do we need to get a shot every year, like for the annual flu shot, or will this last for several years? And that's something that the data will, as data continues to be collected, will enable us to answer that question. So how effective is it? Really effective, but there's still some questions to be answered. Secondly, how safe? So we talked about how getting some soreness, some fever, not feeling so great, that's not really a side effect. That's just your immune system doing its job. But there are sometimes vaccine side effects. There's been a few people who got the COVID vaccine who had an allergic reaction to it. They were treated, they were fine. There's been no severe events such as death from the vaccine. However, getting an allergic reaction could be a risk that someone might not want to take. And oftentimes people think, well, if I have a risk of an allergic reaction versus no risk of an allergic reaction, I'm not going to choose to take that vaccine. However, they're forgetting half the equation there. we're not looking at just the risk of the vaccine versus no risk. We also have the risk of the disease, and which we know with COVID is could be very severe. Months of severely reduced lung function, being on oxygen, neurological symptoms, obviously death. It's a really bad disease. So when we're in a pandemic, there's no zero risk option. You're looking at either risk of the vaccine or risk of the disease. And with the vaccine, very few people have gotten minor symptoms. Compared to with the disease, we know that very many people have gotten severe symptoms. So in that cost benefit analysis, the vaccine side effects are much less risky than the disease side effects or symptoms. And so the vaccine is safe. Even if those few people had gotten the allergy compared to the thousands of people that have gotten the vaccine, the numbers are looking really good for safety of this vaccine. And then finally, how was it made so quickly? That's kind of our big question. That's the title of the talk. That's the question a lot of people have. And so I'm going to talk about three big reasons why it was made so quickly. One is science, one is money, and one is logistics. And we'll look at how robustly and effectively this vaccine was made in the midst of the time schedule we're on. So one is the science. COVID or SARS-CoV-2 is what's called a coronavirus. And there's a family of coronaviruses, which includes SARS and MERS, which are severe acute respiratory syndrome and Middle Eastern respiratory syndrome, which are outbreaks that occurred in the last 20 years of very similar viruses. And because of that, scientists have been doing research on these coronaviruses, on SARS-like viruses, in order to better understand them and prepare to be able to respond by creating a vaccine in preparation for the next pandemic. And this pandemic was no surprise. This article was published in 2015 saying there's a SARS-like coronavirus in bats that could jump to humans. Scientists were predicting this. It was a matter of when, not if. And so when it happened, scientists were ready to get going to create vaccines and treatments. So that was the science of the virus. And then secondly, the science of the vaccine. Like I said, they didn't come up with brand new technologies. They built on previously existing and under development vaccine technologies, such as those for HIV and Ebola and others. So they knew about the viruses, they knew about the vaccine technologies. So when SARS-CoV-2 or COVID-19 hit, scientists were able to sequence it and begin creating vaccines very quickly. Secondly is the funding. For those of you who maybe don't do scientific research yourself, you may not realize how big of a deal this is to us scientists. If I have an idea and I want to get a grant, to get funding to do this idea, to do this scientific research, I have to write a grant, and that takes me a couple months. I was working on a grant earlier today for some of my research. It takes time to write these. Then you submit it to the funding agency, maybe the National Institutes of Health or the National Science Foundation or somewhere else. You wait like 6 months to find out if you get funded, and maybe you don't get funded the first round, and then you reapply, and then you do get funded, and then you finally get the money. Maybe it was 2 years from the time you had the idea till you actually get money to start doing it. With COVID, that didn't happen. It was fast. People were dying so quickly from this pandemic that governments were providing more money for federally sponsored research. Private individuals, Dolly Parton helped fund one of the COVID vaccines, which I think is great. And so people were throwing money at this because everyone recognized how big of a problem it is for COVID to continue to be killing so many people. So researchers weren't waiting months on funding, on limited funding. There was more money, it was coming faster. So instead of sitting around for months, they were being able to do work. And then third reason, the logistics. So how do we do vaccine trials? We have our placebo group that didn't get the vaccine versus our vaccinated group. We can't then go inject them with COVID to do an experiment on who becomes sick with COVID. That's not ethical. So we have our two groups, and then we just let them go about their lives and see if they encounter COVID in the community and whether or not they become sick with it. Well, normally that takes a long time. Even with things like HIV, that can take years to accumulate enough events of people getting the disease to be able to compare your placebo group to your vaccinated group. Unfortunately, because the coronavirus pandemic is so widespread and community levels are so high, they were able to get to these numbers to be able to statistically analyze the placebo versus vaccinated group much sooner than usual. So they had those events of people getting sick really quickly. And so they didn't cut corners on the numbers of people they tested or the science or the statistics. It's just those numbers came in faster because of how prevalent COVID is in our communities. And then finally, pharmaceutical companies took a risk. Generally, a pharmaceutical company, if it's running a clinical trial, is going to wait till they get FDA approval before they start manufacturing, because they don't want to manufacture it and then not get approval and have wasted all that time and money. Well, once again, COVID was killing people so quickly that pharmaceutical companies took a risk. Moderna, Pfizer, they started manufacturing extra doses during their trials. So the second they got FDA approval, they were shipping doses and getting them into people's arms. That doesn't usually happen with vaccine development. So that's another reason it got sped up. Obviously, there needs to be more done to get more vaccines distributed to people, but pharmaceutical companies took that risk and that gave us a jump start. So here, this is from the New England Journal of Medicine, showing how traditional vaccine development, you have your science, your preclinical development, your clinical trials that measure safety and dosage and efficacy. Then you get FDA licensure, then you produce. All of those steps happened for COVID. They didn't cut any corners on steps. It just happened in a condensed timeline. The preclinical development, the science, that was already kind of done before, like I mentioned. The phase 2 and 3 trials happened quicker because people were getting COVID so fast in the placebo group. The production started before they got licensure. So the combination of all of these factors really shortened that timeline without shortening the robustness of the science. So no corners were cut in the science. These are really safe and effective vaccines. So to kind of answer our question, is it a race? What kind of race is this? Is it a sprint or is it a marathon? Even though it's only been a year fighting COVID, this vaccine development is based on decades of research about coronaviruses and really centuries of research about how the immune system and vaccines work. So really it's a marathon, and scientists have been running this marathon for a long time before COVID hit, and they were able to produce data really quickly, and then they'll continue running this marathon, collecting more data on COVID and helping prepare for other pandemics that might happen. So really in summary, the evidence shows that the COVID vaccine is based on robust scientific research with a foundation of lots of research on the virus and on vaccine technologies. It is safe and effective based on these clinical trial data. And it is the tool that we can use to develop herd immunity. And this is a phrase we've probably heard a lot. What is herd immunity? Basically, if someone's infected and nobody else has immunity, that disease is going to spread in these little red figures here. However, if lots of people are immune because of the vaccine, they have that strong immune system to help fight it, that's shown in green, then there's very little places for that virus to go and it eventually gets snuffed out. The way to achieve herd immunity is through vaccination. If you just let the disease run its course through the population, the collateral damage is too great. Too many people will die as a few others develop immunity. With the vaccine, people can develop immunity without that contraction of COVID, without getting those symptoms, without dying. And so it's the safe and ethical way to achieve herd immunity. And like we said, there's still a long way to go with COVID. We have to get this vaccine to lots of people, and that takes time, and it will take some time of us still social distancing and mask wearing until we get this herd immunity and begin to slowly snuff out the places for COVID to go and multiply in the population. So with that, I would love to answer your questions. Like I said, I'm passionate about scientific dialogue and want to hear your concerns and have a conversation about that. My email is here. You can always reach out to me at any time. But also I'm going to stop my share and see what questions you guys have now.
Okay. Well, we don't currently have any in the chat. So what I'm going to do is unmute everyone so we can talk more freely, and then I'll just open it up to anyone who wants to ask questions. Did I unmute or? No. Oh, participants to unmute. Yep. Okay, so I think you should all have the ability to unmute yourselves now. So we'll just open things up to questions. So.
Hi, you hear me?
Yeah, Barbara, I can hear you.
Okay. I'm wondering about the testing and the statistics that are coming back that may be age related. My father is 94 and we haven't discussed this yet, but he may be concerned about having this virus vaccine because of his age versus somebody that's in their 60s or 50s?
Mhm. Yeah, so great question. They tested this vaccine down to 16 years old is what it's approved for. I think I can't remember which one, but Moderna and Pfizer, I think one of them tested down to 16 and one tested down to 18. So it's actually kids that they haven't done a lot of the research in. They've done testing in all of the other age groups, and the results have come back comparably for all those different age groups. So I wouldn't have any concerns about anyone who's older. And honestly, I wouldn't have concerns about like a kid either. I don't think there's any problems. They just haven't done the data yet on kids. But on older people, they've done the data.
Okay, is there a place where that sort of statistical analysis is readily accessible?
The CDC is always a go-to place for all information on COVID. And I can look up and see that. So Pfizer and Moderna have published their results in scientific journals. I wouldn't, that's accessible. I wouldn't necessarily say it's easy to interpret if you're not familiar with the confidence intervals and the statistics. I can get a little boggled by it. I don't know if there's a place where they've simply laid out in this age group, it was this percent effective. It's in this age group, it was this percent. I would look up at the Pfizer and Moderna websites. They probably have some data. I showed you those charts and I was just able to Google that to find that data. But the CDC, like I said, is always a good place to go for up-to-date information. They've been posting a lot about the vaccine and data recently.
Okay, thank you. Because if I can send
I'll throw my email address in the chat if you want to email me and continue this. And if I can continue to look for that data that you're looking for, Barbara, and see if I can find it laid out clearly and get that sent to you, if that would help your father feel more secure.
Yeah, because it would, I mean, he's pretty darn sharp, but he would need to be able to, I don't think he's going to read a scientific journal. You know?
Yeah. So yeah, feel free to shoot me an email if you like, and I can continue and help you find the data that you're looking for.
Thank you.
Mm-hmm.
And all the vaccines that they give out now to I'll say the older people, do they put some placebos in amongst this just to keep their percentages of this and that?
Great question. So they have unmasked or unblinded the clinical trials. So when they did the research, those clinical trials, the placebo versus the non-placebo, that was double blind, meaning that the person who got the shot didn't know which shot they got, and the researchers analyzing the data didn't know what shot they got, so no one could put their preconceptions into it. They have since, at least for one of the trials, including the Oxford trial that's they just wrapped up, begun to unmask that. So then people know, like, hey, 6 months ago you were in the trial, you actually got which shot. So the reason they're telling people that is so that the people who did get the vaccine shot don't go ahead and get another vaccine shot and take that away from someone who still needs the vaccine because there's limited doses. So they're not continuing to do placebo shots because basically anyone who's unvaccinated is kind of like a placebo. We can compare vaccinated versus unvaccinated people. The results were strong enough that they don't need to continue the trial in the same setup with blinded groups because they got their data that was statistically significant with the numbers that they needed to make their 95% effective claim. So now we can just go ahead and vaccinate people. The long-term tracking they're going to do is looking at things like I said, like, do they ever become COVID positive, even if they never become symptomatic? How long does this immunity last? Things like that. But that will all be on vaccinated people. We don't need to compare vaccinated versus unvaccinated in the same blind, double-blinded clinical trial that was done before. Does that answer your question?
Yes, I think so. That what the vaccines that are being given out now are not containing any placebos. Is that correct?
Correct. Yeah. So they're not part of the clinical trials anymore in the same way. They are just the vaccine doses.
Thank you.
Yeah.
Very good to know.
Yeah. Good question. Any other questions?
I was going to say, I actually had a question. Like, you hear about how there's multiple different vaccines. We have the Moderna, we have the Pfizer. There are other, I can't remember the name of one, but I know Russia has one. I'm assuming China also has a version. Is there, do you happen to know what the difference is between these different vaccines?
Yeah, so the Moderna and the Pfizer are very similar. They're both just that naked piece of mRNA that codes for what's called the spike protein, which is a protein on the surface of COVID. So your body will if you get the actual COVID virus inside your body will say, oh, I recognize that protein on the outside. I can mount an immune response. The Oxford AstraZeneca one, which they're doing a clinical trial, and that one is probably soon to be approved as well. That one is in that viral vector. So it's a little bit different, as is the Johnson & Johnson. It's also a viral vector. So they're kind of in two different groups now, the ones that are getting approved. They all are targeting the spike protein though. The reason the spike protein is the target is because one, it's on the outside of the virus, so your body can see it. And then secondly, it's the one that's needed for the virus to enter your cells and infect your cells. So if your body mounts an immune response against it, it'll make all those antibodies that will bind all over those spike proteins, and now the virus can't get into your cells and can't do anything. And so that's why that's kind of the target of pretty much all of the vaccine strategies that involve an RNA component in them. Does that answer your question, Jennifer?
Yes, thank you.
Awesome.
We also, it looks like we have a write-in one. I don't know if can you see it in the chat?
Yes. Is the vaccine similar to the flu shot? Okay. So that is, there's not a strong answer to that yet in the scientific community. It's kind of more like the flu shot, I will say, in that for the people who did get COVID, that 5% who got COVID after being vaccinated, their symptoms were more mild than the people who got COVID and hadn't been vaccinated, had the severe symptoms. People with the vaccine had the more mild symptoms. But we don't know how, like the percentages of how strong that is. And so that's something that they need to test is for the people that didn't get COVID symptoms at all, was it because they just never got COVID, or did they get it and they were just asymptomatic? And so that they need to do COVID tests on people who have been vaccinated more stringently. And it's just, there's a lack of availability of testing that hasn't given us that data yet, but that they're doing the experiments to be able to answer that question. Because that's a really good question for us to know is, does it prevent you from getting COVID at all? Like the polio vaccine you mentioned there in the chat, or do you just get less severe symptoms? It's good if you get less severe symptoms, right? That can keep you from dying, but you could be spreading it to other people. And that's really the question we need to figure out is, can you spread it to other people or not after getting vaccinated? Do you still need to be wearing a mask after getting vaccinated? Those are the questions they're trying to figure out. I unfortunately don't have a strong answer for you, Alyssa.
So, can you hear me?
Yep.
This might be kind of a out there question, but how does COVID compare to what was the Spanish flu of 100 years ago?
Mm-hmm. So, yeah, that's a great question. In terms of the disease course, COVID is a really nasty virus. It obviously infects your lungs like the flu does, but also people with COVID are having neurological symptoms. They're having problems with their endothelial cells, which is their blood vessels, basically. There's clotting. It's a really widespread symptomology, which really affects people. So in terms of a person getting COVID versus getting the Spanish flu, I would argue that COVID is worse, just in terms of the things that it can do to your body. In terms of the numbers, the Spanish flu of 100 years ago, the 1918 pandemic, really ravaged people and killed a lot of people. But if we were to have that exact same virus hit today, it would kill fewer people because our medical technology is a lot better than it was 100 years ago. So the fact that it killed a lot of people, part of it was because it was 100 years ago and our medical care wasn't as good. COVID is arguably a worse disease on an individual level, if that makes sense. But they're similar in terms of they're both pandemics. They both, wearing masks prevents them. We can look at historical images of people during the 1918 pandemic wearing their flu masks, just like we wear our COVID masks now. And so there's similarities because they're both airborne viruses like that. But there's differences in the virus themselves. Does that answer your question, Janine?
It does. Thank you.
Yeah.
So I'll ask another question. And
Yeah.
Even though the basic technology is the same with the Moderna and the Pfizer vaccine, my understanding is that if you have one dose of one or the other, your second dose needs to be the same manufacturer.
That is, yes. So that 95% effectiveness is based on people getting 2 doses of the same manufacturer at the right dosing level. If you just get 1 shot, it's only like 50-60% effective. And the dosing does matter. So for example, the Oxford AstraZeneca trial, they had a couple different outcomes depending on what dose they gave people of the virus. And do we give a small dose and then a big dose, or a big dose and then a small dose? And that's one of the questions they're trying to work out in that vaccine. So yes, if you get a dose of one manufacturer, you should get the second dose from the same manufacturer at the dosages that gave the good results in the clinical trial. Vaccines, even though the concept is very simple, let's introduce a portion of the pathogen to activate your immune system. In actuality, getting that to work right is very tricky, which is why there's dozens of COVID vaccines under development that haven't been approved yet. And even my colleagues at CSU are creating other strategies that might eventually get approved but aren't yet, because it's actually really tricky in actuality. So yes, like you said, Barbara, you want to get the first and second dose on schedule from the right from the same manufacturer. Whichever one that is, shouldn't be mixed and matched, or don't just take 1 dose, because that won't be as effective as the 2.
Thank you.
Mm-hmm.
Okay, it looks like we have a question in the chat. I'll go ahead and answer this one. Is this talk being recorded? And the answer is yes. We are recording it, and we will be uploading it to our YouTube channel sometime tomorrow.
I have a question. Is it ever going to be possible to get herd immunity if we don't get a majority of us vaccinated?
Yes, but the collateral damage would be way too great. Basically, the way to do that would be everyone would have to get COVID. And with the percentages of people that die who get COVID, even if it's just a 1% death rate, that's still, what's 1% of the American population? That's what, like millions of people still, right? And so technically, yes, but it's not ethical or right for that to be the strategy to get herd immunity. There's never been herd immunity established without a vaccine or a mass casualty event like the Spanish flu or the Black Death or something. So technically, yes, it could go through the whole population. That's not ethical or right.
Right. So for all the people that are in the 50s and 60s that are saying they're too afraid to take the vaccine, that's going to be more detrimental to the people that are in the 60s and 70s and taking it and still having to stay in because the others won't get the vaccine.
Yeah. And that's really what I was mentioning with you have to weigh, like, maybe you're a little scared to get the vaccine, but what if you get COVID? And that's really the question.
For sure.
That is helpful if you're having friends or family that are concerned about them. Help them think about it's not vaccine versus nothing, it's vaccine versus COVID. And also thinking about others. When you get the vaccine, you're more likely to be able to protect others than if you don't.
Right. Okay, thank you.
Any other questions? Well, if there's no more questions, I've put my email in the chat. Feel free to reach out to me if you want specific data or evidence. I can find that for you and send that to you. I really have enjoyed hearing your guys' concerns and ideas, and it sounds like a lot of you have done some looking into this before, and can be talking to your friends and family and helping them make informed decisions. And I think that is awesome. I love that it's not just us academics and scientists talking about this, it's lots of people, and that's what we need. So I am really happy to have gotten the chance to talk with you guys tonight, and then any further questions, feel free to reach out to me by email.
So I have one quick question.
Yeah.
Sorry, one more question. Just, are you doing this around other places besides just for us? I'm hoping.
You are the first people that have asked me to come talk. So I haven't yet, but I would be happy to if you're part of other groups that are interested in me coming and talking to them about this.
It just seems important to have science educators be talking about it, right? So.
Yep, okay. I agree. Obviously, I'm a little biased because I am a science educator, but yeah, if you guys have, if you have friends, family, other groups that are interested, feel free to reach out to me.
Thank you.
Mm-hmm.
All right. Okay.
And I will also say that the CSU microbiology department has many really great researchers, even if they don't specialize in science, education, and communication like I do. They are in the lab working on COVID and other similar problems, and they are great people who've done some, if you look at CSU's website, they've done some articles and videos and things with a little bit of information as well. So if I don't know the answer to something, I can always point you to colleagues who do know that answer.
Thank you very much. Do you want us to hit the leave button now? Or
Well, yeah, and if there are no more questions, I just wanted to thank you again, Nicole, for taking time out of your evening to do this talk with us. And for those of you who are interested, a recording of this talk will be uploaded to the Clearview Library District's YouTube channel sometime tomorrow. So yes, you can watch again, share with your friends. But I will, if there are no other questions, I will go ahead and end this meeting for tonight.
Thank you so much, Nicole.
Thank you all, and thank you, Jennifer.
Yeah.
Thank you very
Thank
much.
you.
Yeah.
Bye.
Bye.
Bye-bye.